Okay, guys, we're going to go through and discuss the types of substitutions we're going to expect based on the nucleophile. Okay, and then based on the different types of substrates we're going to be looking at. Okay, so the alkyl halides. We have methyl, we have primary, secondary, and tertiary substrates. Okay, and so this is a way for you to both look at the nucleophile and to look at the substrate system to decide if there's even going to be a reaction, okay, or what type of reaction the substrate will undergo. Okay, so the first thing we have is we have this nucleophile, and my nucleophile is methanol. Methanol is a neutral, weak base. And typically when we use these types of solvents, when we use these types of nucleophiles, we're looking at some sort of symbiosis reaction. Okay, and so looking at my methyl substrate, okay, I can see here when I'm starting with my methyl substrate, okay, if I have a neutral poor nucleophile, okay, methyl, which by the way can only undergo SN2 reactions, and SN2 reactions need a stronger, at least at the very least, charged nucleophile, okay, this methyl halide will not undergo any reaction with methanol. So the answer for this top one would be no reaction. Why? Because it can only do, oops, sorry, my brain's getting SN2. Okay. And the funny thing is, we're going to look over here, okay, at the next substrate, which is a primary substrate. And again, primary substrates, now they can undergo E2, but in terms of substitution, okay, they can only undergo SN2. And again, you know, we know that methyls can only do SN2, primaries can only do SN2 and E2. So when I go back up here and I look at, say, okay, well, what's favored for E2, you know, I can only use strong bases. Okay, they can be strong, not sterically hindered, or strong and sterically hindered. Okay, and so again, an alcohol is not a strong base, regardless of its hindrance. Okay, it's still not a strong enough base to undergo SN2. Okay, and it's certainly not strong enough for E2. So again, this is no reaction because, again, I need a strong base. For E2, or at least I need a charged base for SN2. Now we're going to take a look at our secondary substrate. Okay, so again, we're going to go back down here. We're going to look at our secondary substrates, which are here, sorry. And what I can see here is that, okay, secondary substrates, okay, if I have a neutral poor nucleophile, they can undergo SN1 and E1, okay? So check, okay? I can form an SN1 product and an E1 product. We're gonna look at our tertiary substrate. Okay, tertiary substrates are actually better at SN1 and E1. Okay, again, this is my nucleophile, so I don't need a strong nucleophile because the rate determining step for SN1 and E1 is what? The formation of carbocation. So we all know that tertiaries form carbocations the fastest. So check, I'm going to see an SN1 and E1 reaction. Okay. So again, the mechanism for both of these is exactly the same, but I'm going to go ahead and go through them just so that you can get an idea of what you can expect. For the secondary substrate, again, we're going to see SN1 and E1. In both of these reaction mechanisms, the rate determining step, it's a leaving group leaving. And so I'm going to do two different reaction pathways, one for SN1, one for E1. Okay. Once I form this carbocation, okay, then we'll see either the substitution or the elimination reaction occur. Okay, so what I'm going to do over here, the top, I'm going to go ahead and do substitution. Methanol in this case will attack the carbocation. I will form this new bond between the oxygen and the carbon atom. It will look like this. Okay. It's a positively charged species. Hold on. It's a positively charged species. And so the halide that I lost in this first step, okay, because remember the halide is going to take the electrons with it, with a halogen, and so it's going to come off as a halide, okay, it can come and remove the proton in this so-called deprotonation step. And what we're going to form here is, oopsie, is this ether. So this will be the final product. Okay, is that ether right there? So that would be the SN2 pathway. I'm sorry, that will be the SN1 pathway. Now we're going to look at the the E1 pathway. Okay, where I'm going to form this carbocation, and we know that these beta hydrogens can be eliminated. We know because of hyperconjugation and the inductive effect, the carbon hydrogen bond is being weakened by neighboring carbons. And so again, depending on what you're used to seeing, the solvent can come and remove this. And so this is going to be the product of this particular reaction. This is my E1 product. And again, remember that we're also going to see what? We're also going to see plus HX, okay? It's a byproduct. We don't typically write it because it is a strong acid because all of our leaving groups are very weak bases. They're either iodide, bromide, or chloride. And so we don't typically see this in solution because it's going to be disassociated, okay? And so again, this is looking at the nucleophile. So let's look at a little bit stronger base, okay? That's going to be a nucleophile. Again, now we're going to look at sodium cyanide. We're going to look at our different substrates, and we're going to look at what type of reactions they can undergo. So again, I have methyl. I have a weakly basic charged nucleophile. That's great. So what I'm going to see here is I'm going to see SN2. How do you know that this is charged? Well, again, remember, just cross out the sodium. And so my cyanide is right here. Okay. Cross out the sodium, which I just showed you, but you didn't get to see. You cross out the sodium, and we know that cyanide is an anion. So we're just going to write it off to the side here. How do we know it's not a strong enough base to undergo E2? Well, a lot of confusion with cyanide. Remember, cyanide is the conjugate base of an acid. So by definition, it's not a strong base because it is the conjugate base of an acid. In other words, acids do not occur, okay? Species are not considered acids unless there's at least some dissociation that will happen in water. And so by definition, this is a weak base. Certainly stronger than iodide, certainly stronger than a lot of these anions we've looked at, but it's not strong enough to undergo an E2, okay? And so that's how you know that. So going to my next point. For primary substrates, again, weakly basic charged nucleophile, only SN2. So for this one, I'm going to see an SN2 reaction for my primary substrate. Okay, now I'm going to take a look at my secondary substrate. Now, secondary substrates with weakly basic good nucleophiles charged, okay, can undergo all the reactions except for E2. And so this is the only time where you're going to have to look at your solvent, okay, to decide what pathway do I go? Okay. And so we're going to have to take this and we're going to have to delimitate it even further, that if I have a polar aprotic solvent, I'm going to see SN2. If I have a polar protic solvent, I'm going to see SN1. And of course, E1. Okay. And so this is the only time with a secondary substrate, okay, and a weakly basic charged nucleophile that you actually let solvent determine the course of the chemical reaction. Tertiary substrates are a lot more straightforward. They're incapable of SN2. Again, we've already discussed that cyanide's not a strong enough base for E2. So the only pathway, okay, that we can see, okay, tertiary substrate, weakly basic charged nucleophile, we're going to see SN1 and E1, okay? And so again, let's take a look at these reaction mechanisms. For methyl, okay, CH3X, actually, I'm just going to redraw it over here like this. CH3X, let's just assume that I give you sodium cyanide. Oops. Okay, so let's look at this mechanism between cyanide and our methyl halide. So again, we know that cyanide is going to come in. It's going to come in from a backside attack. Do your best to show that on the exam. I know it's not always easy, but again, cyanide leaves. The bond between the halide and the carbon is broken simultaneously. Since this is not a chiral center, you don't have to show me the inversion because it's not going to happen. Okay, and you're going to form this new bond between cyanide and our methyl group in this case. And I'm going to form this new compound that is actually called acetonitrile, and it's one of your polar aprotic solvents. So this right here, okay, it looks like this on the chart is aceto. Oops, it doesn't look like that. It looks like this. This is acetonitrile. So fun fact. All right. So again, going over to our secondary substrate. Going over to our primary substrate. Again, okay, oopsie. So when we look at this, okay, primaries with a weakly basic charged nucleophile are only going to undergo SN2. Again, okay, and it's not a strong enough nucleophile to facilitate E2. So again, very easy substitution reaction. Okay, I'm going to form, again, this new bond between carbon and this cyano group. It's called the cyano group. So just in case you're wondering, remember that carbon is sp hybridized. So don't bend my angles when they're supposed to be linear. Okay, don't bend my angles when they're supposed to be linear. All right, so secondary substrates, again, this is where we start to see a little bit of confusion. Okay. So again, this is the only time that the solvent is actually going to be a factor. So I've got two examples of where I have different types of solvents. I have a polar aprotic solvent in DCM, it's dichloromethane. Okay, and then I have a polar protic solvent, okay, in this secondary amine. So going back to what I was doing earlier, okay, SN2. Voila. Actually, let's make this a little interesting. Let's actually make this a chiral center, right? I haven't done any examples of those. So let's go ahead and just make this a chiral center here. Okay. So again, I'm going to have the backside attack, do the best you can to show it. And then of course, my new bond will be inverted. Okay. And then if you want to, you can just draw your cyano group like that. Okay, you can draw your cyano group like that. All right, now what is this going to look like with my secondary substrate with a polar protic solvent? So let's do what we did up here. Let's go ahead and let's make this guy chiral. So this is going to be SN1, E1. So both the pathways are going to start the exact same way. I'm going to form our carbocation. Cyanide can attack this empty p orbital either on the top side or the bottom side. So I'm not showing this happening, attacking top and bottom at the same time. I'm just showing that these are two options. Okay, these are two options. And so what I'm going to get for this particular reaction, whereas in the SN2 reaction, I only formed one enantiomer, here I'm going to form both enantiomers. And so we're going to say the mixture is racemic. Okay. All right. That's the SN1 approach. So now we're going to look at the E1 approach. Again, it's the exact same mechanism, same rate determining step, only now I have two different beta hydrogens. I've got this beta hydrogen here. Okay. And I have this beta hydrogen on the terminal carbon. So because I have a non-symmetrical carbocation, okay, we can expect two different elimination products in this particular case. And so I'm going to have X minus come, remove this. Okay. So I'm going to form, in this case, this alkene here. Then I'm going to have another equivalence of X minus come and remove the terminal beta hydrogen. So in this case, I'm going to form that product there. And remember, this is the major elimination product. Because it's the more substituted alkene. Okay. Now again, my tertiary substrate, weakly basic nucleophile, it's incapable of undergoing SN2. So solvent is kind of irrelevant here. And again, cyanide is not a strong enough base to do elimination. So the only pathway I can expect here is SN1 and E1. So just like we saw above, for both of these pathways, the very first step, of course, is the leaving group leaving. Okay, I'm going to form this intermediate species. I'm going to do substitution first. So my cyano group can come in. I'm going to form, again, you just learned a new functional group. I'm going to form this nitrile with my new bond being between the center carbon and the cyano group. Okay, so second, E1. So again, it's the exact same first step. Leaving groups leaving. I'm going to form the exact same carbocation that I formed in the SN1 step. Now, I'm going to have this beta hydrogen removed, just like above. I'm going to have X minus come and remove it. So in this case, you're going to form, oopsie, you're going to form this elimination product. Okay. So again, that's the trickiest of all of them, right? If you go back up here and you look at this chart, right? You go back up here and you look at this chart, it's the weakly basic, okay, but charged nucleophiles, oops, over here. It's the weakly basic charged nucleophiles that will give you the most issues, because this is a lot more substrate dependent, right? Okay, and it's also the only case where you need to take a look at solvent in terms of a secondary substrate. Okay, all righty, next one. Now we're going to look at our strong non-sterically hindered bases. Okay, our strong non-sterically hindered bases. And these bases are only capable of SN2 or E2, again, depending on the substrate. Okay, only SN2 and E2 depending on the substrate. So I'm going to go take a look at my primary substrate. Okay, strong non-sterically hindered bases. Oops, that's primary. I meant methyl. Strong non-sterically hindered bases. Strong. Okay, SN2 only. Again, you can't have an elimination reaction with a methyl group because why? You can't form a carbon-carbon bond if you only have one carbon. Now we're going to take a look at our primary. Okay, we're going to see a combination of SN2 and E2. Okay, SN2, E2. Same thing we're going to see with our secondary substrate. Non-sterically hindered bases, we're going to see SN2 and E2. Okay, and so again, okay, we're not going to ask you which of these are more favored in terms of elimination or substitution. Typically, when we see elimination, it's favored what? The more substituted the substrate because of the transition state species, okay, and typically heat, okay, helps us with elimination products, favor elimination products, okay? But our book doesn't go into that, so I'm not going to go into that. Tertiary, okay, tertiaries are incapable of undergoing SN2. So the only thing we're going to see is the E2. And out of all of these substrates, this, of course, is going to be the fastest E2. Okay. Again, these reaction mechanisms, very straightforward. Okay. Just like before. So this is an ion. So, of course, it's going to disassociate. So my methoxide will come in, backside attack, kick off my leaving group. And I have formed a new bond between that carbon, which I just drew as one too many. I'll just draw it like this to keep it clear. Okay. Between this carbon and this ethoxy group. So basically I made this ether. Okay. Primary, we said it's going to undergo SN1. I'm sorry, it's going to undergo SN2 and E2. So these are in competition with each other. These are not happening, quote unquote, at the same time. In other words, with the same rate. They are happening in the same flask, but again, these are in competition with each other. So they are not going together, so to speak. Okay, so I've made diethyl ether, which is again one of our solvents. Okay, this is one of our polar aprotic solvent. And actually, look at that. I inadvertently chose diethyl ether as a polar aprotic solvent to be using for this reaction. So yeah, it's funny. So that's the SN2 reaction. So let's look at the E2 reaction. Again, this is a concerted reaction. Just because it's concerted doesn't mean it's the same as SN2. So again, we're going to have beta elimination. In this case, there's only one beta proton. Everybody's going to leave. I'm sorry, deprotonation step. Leaving group leaving and pi bond formation is all happening simultaneously. And it's kind of weird, but this is our product. If you're getting confused because I'm using skeletal structures, go ahead and feel free to write them out. I could care less. Okay. Same thing with secondary. Secondary is going to undergo SN2 and E2. Now, because it's secondary, it's probably going to undergo a little bit more E2 and a little less SN2. Okay, but again, your book doesn't talk about that, so I'm not going to talk about it. So we're going to do our SN2 first. Oh, let's do like we did upstairs. Let's go ahead and turn this into a chiral center. Okay, so we're going to get inversion. We're going to form this new bond here. And I'm now going to form this chiral ether. Okay, I'm now going to form this chiral ether. And so again, the E2 version is again no different from what I've shown you before. Okay, once you can wrap your heads around these bases, your life is going to get a lot easier. Okay, I'm not going to lie. Okay, these bases have a tendency to make your life's a living hell, and you all tend to focus on the DMSO, that should be DMSO. You guys have a tendency to focus on the solvents and not the bases, okay? Bases first, then substrates. And so again, we're going to go ahead and we're going to draw this with the two different beta protons. Copy, paste, paste. Go ahead and, shoot. Sorry. I know this is not as slick as some of those other YouTube videos, but I can pretty much guarantee it's all right. Let me just put it over here. All right, so again, this beta proton here versus this beta proton here. Okay, my ethoxide will come in. Remove this one. Okay, form the pi bond, kick off the leaving group. Okay, and I will form this major elimination product. So the elimination products are the same in terms of major and minor for E1 and E2. That doesn't change because you're always going to form the more stable alkene in this type of an E2 reaction. Okay, and so I'm going to get these two products as well. Okay. All righty then. So next, we're going to look at our tertiary substrate. Now, tertiary substrates cannot undergo SN2. So with this strength of a base, okay, I can't do SN2. I can only do E2. So, I mean, again, it's kind of funny that there's a lot of overlap between these reactions. You're probably sitting there thinking, well, she's shown me the same reaction over and over again. And the fact of the matter is I have, because some of these substrates, given the different strengths and bases, can only undergo specific reactions. So again, in this case, so ethoxide will come in, it will form my pi bond, it will kick off my leaving group. Okay, and out of all of these substrates that I've shown you, this will undergo the fastest E2. Okay. Alrighty. The last thing we're going to look at is the last type of base / nucleophile you can expect to see. So these are my strong sterically hindered bases. These are E2 only, unless I have a methyl substrate. Again, methyl substrates cannot undergo elimination. And here's some examples of these. Shoot, I forgot to, this is the older one. DBU and DBN is what I've added to the list online. So let me bring this over real quick. So DBU, DBN, okay, and I will be using the abbreviations on the exam. Okay, for DBN and DBU, I will be using the actual structures of the other strong sterically hindered bases. Okay, but again, you have to understand the difference between a base, sodium ethoxide, okay, versus its conjugate acid, which is ethanol. Going back over here. So this is very straightforward. SN2 only for my methyl substrate. Because this is a strong sterically hindered base, the rest of these substrates will only undergo E2, so beta hydrogen elimination. Okay, and I've already showed you these mechanisms a bunch of times, but you and I both know that being able to look at these over and over again probably wouldn't kill you. So I'm just going to go ahead and do them all, because I want you to show you again that it doesn't matter, okay, what our base or nucleophile is. Once you determine the pathway, the mechanism is always the same. Okay, with this next one, my primary, I can only do E2. So again, my tert butoxide, which is this guy right here, is going to come in, remove this beta proton, form my pi bond, form this substrate here. which is an alkene. Okay, again, if you're not sure, go ahead and draw your carbons in like that. You can see where they're there. Same thing over here. I'm going to come and I'm going to remove this beta proton here with my secondary substrate. Potassium, I'm sorry, butoxide rather, is going to come in and remove it. Feel like what happened to the potassium? It's still there, right? It's just dissolved in solution. We don't care about it anymore, right? We need it because we have to buy potassium butoxide. We just can't buy butoxide, right? You can't call up and order an anion or a cation for that matter. Okay, so we're going to form this product here. And it doesn't matter which one of these protons I eliminate because this is a symmetrical substrate. So I'm going to eliminate this one down here. I'm going to form my pi bond. I'm going to kick off my substrate. Oops. I'm going to redraw this so it doesn't look like crap. And again, this is my new bond here. Okay, and so that is a summary. Okay, that is a summary of what you need to be looking for. Again, okay, first thing you look at, type of base. Okay, you look at the type of base. Then you look at the substrate. Okay, then you look at the substrate. Certain substrates can only undergo one reaction. Some substrates can undergo different reactions. Okay, but it depends on the conditions. Only under one particular condition, only once, do you ever look at the solvent. Okay, so again, I know a lot of people look at the solvent because it's just easier to do, but try to avoid doing that because it can put you on the wrong path. All right, that's it. See you later.